Hello, thank you for attending this presentation on the structural parameterization of kinetic umbrellas under hydrostatic inundation. I am Shengzhe Wang from Princeton University. Kinetic umbrellas are four-sided hyperbolic paraboloidal or hypar shells inspired by the architecture of master builder Félix Candela. Unlike traditional umbrellas that were designed by Candela, we incorporate a hinge at the vertex, which allows for tilting. When kinetic umbrellas are placed adjacent to urbanized shorelines, they provide shade and shelter without limiting access to the coast. This is unlike that of a typical flood wall. Due to this hinge, they can be deployed to form a physical barrier to protect communities from storm surge flooding. Hence, kinetic umbrellas are an example of adaptable architecture, which represent the amalgamation between structural art and coastal hazard engineering. This talk will focus on the influence of various geometric and design parameters on the structural behavior of kinetic umbrellas under hydrostatic inundation. The geometry of kinetic umbrellas considered as part of the study measure 8 meters by 8 meters square in plan and were tilted at an angle of 65 degrees to the horizontal. This results in a total deployed height of 7.25 meters. The parameters we are varying consist of the level of hypar warping, or the R/A ratio, with R being the rise and A the plan area. Also, the water inundation height from half of the deployed height to the entire deployed height. And finally, the lateral stiffness of the supporting column, which we will call the lateral hinge stiffness. We employ finite element modeling via the software SAP 2000, utilizing a 100 millimeter thick concrete shell reinforced with glass fiber reinforced polymer bars. The design of thin plates and shells are often governed by out-of-plane bending and shear effects. When examining the maximum moment and shear forces, it is seen that large values exist for a flat plate without hypar warping across the entire range of hinge stiffness, as circled in the diagram. It is seen that through the introduction of hypar geometry, a significant reduction in moment and shear is observed. Further increases in warping, however, only yield modest reductions in the critical demands. It is also witnessed that bending and shear are inversely related to the hinge stiffness. The distribution of maximum moment and shear demands are further explored. At small levels of warping, maximum demands are located about the hinge zone. This reflects the behavior of continuous slabs spanning over localized supports. However, as the level of warping increases, critical demands shift towards the lower panel due to the umbrella's increased resistance against deformation. This is especially the case around the vertex. Next, a case study was adopted to assess the feasibility of kinetic umbrellas from a structural engineering perspective. An umbrella with R/A equal to 0.03 inverse meters was selected. This umbrella was subject to the maximum possible level of inundation matching the entire deployed height of 7.25 meters. Furthermore, a 1 meter square concrete column was adopted for lateral support. The umbrella was assumed to be 100 millimeters thick, fabricated using high-strength concrete, and reinforced with a mesh of 16 millimeters GFRP bars spaced at 100 millimeters. A 125 millimeter parallel flange channel, or PFC, provides perimeter stiffening. The bending capacity was determined using Response 2000, while the shear capacity was calculated through the Canadian design standard S806-12. The results from moment curvature analysis demonstrate that the bending capacity exceeds that of the demand. However, shear demands are in excess of the concrete capacity along the edge and within the lower panel. This is where hydrostatic forces are highest. Therefore, additional transverse shear stiffness would likely be required within the lower half of kinetic umbrellas. Note, however, that shear demands along the longitudinal perimeter can be assumed by the steel PFC frame. In conclusion, it is demonstrated that hypar geometry can significantly reduce out-of-plane bending and shear demands within thin shells. In the context of kinetic umbrellas, an R/A ratio of 0.03 inverse meters appears to be optimal. In addition, increasing the lateral stiffness of the supporting column acts to further reduce bending and shear demands within the shell. Finally, kinetic umbrellas just 100 millimeters thick can be successfully designed to resist hydrostatic inundation, matching its entire deployed height of 7.25 meters. This is taller than a two-story building. For more information, we refer you to our recent publication in thin wall structures. Thank you for attending this presentation.